Okay, let's get started. So hopefully people can hear me. I guess if not, you can't hear me saying this, so whatever. We're going to be working through this notebook on the site called Google Colab. I'm going to pop the link to this in the chat. But if anyone joins late, they might not see the link. So if anyone's asking about it, just tell them, look at the bottom of the screen, and the link is down here. So you can click that to open it. And this is what we're going to be walking through in today's session. Yeah, go ahead and record it. That's completely fine. I think we'll also have a recording up somewhere on the WarwickHack site or somewhere later. Okay, so we have this notebook open. Where are we? So this is a site called Google Colab. And it's an online platform for running Python code. Basically, Python can be a pain to set up. And so rather than trying to do that, we're going to do it all in the cloud. Google kindly give you a load of free resources to run your Python code. All you need is a Google account. So if you go on to this site, you'll be able to use it. If you try to run anything, it will ask you to sign in with a Google account. If you don't have one of them, you might want to make one now while we're just running through the introductions. So what are we going to look at today? The session is all about machine learning. We're going to learn what machine learning is. We're going to learn about a specific type of machine learning model called decision trees and random forests. We're going to make our own machine learning model, and that's going to be based on trying to predict people's income levels based on characteristics like their age, their race, their education level. And then we'll talk a bit at the end about how do we know if a machine learning model is working and how we can make them better by tuning them. And so the style of this teaching is going to be fairly interactive. I'll be asking a few questions as we go through. I'll be filling in this notebook. It's currently basically blank. And you're welcome to fill it in as we go too, so you have your own copy of things. Or you can just watch, and at the end, if you didn't have time to fill things in, there's a link at the top to a completed version if you just want to run it without filling it in for yourself. So it's going to be very practically focused. I'm not going to get into too much of the theory, but more exactly how you can do machine learning. It's going to be very light and kind of focus on exploration more than memorizing things. So we're going to be using Python. I'm not really going to explain what Python is or kind of why we're doing the things we're doing. We're going to focus on the higher level concepts of what machine learning is like, just kind of explore what you can do with Python. And if you want to learn more about Python, then we run courses on beginner's Python and kind of data scientific Python, which includes machine learning. I'll mention those more in a second. So I am the president of the Warwick Data Science Society. I believe there are 2 other talks being ran by Warwick Data Science Society as part of WarwickHack. One early today and one at 7 o'clock by one of our tech people, Matthew Bosley. Great guy, really talented, so make sure you check that out as well. So yeah, definitely follow Warwick Data Science Society, Facebook, LinkedIn, YouTube. We have lots of teaching courses, all free, very high quality. So make sure you're following at least one of these platforms so you know when we have these running again. We have lots of events for networking, for kind of just learning about data science from academia and industry, student-led talks, workshops, and a lot of research projects. If you are short of an internship, we run research projects and we will be doing so over summer. So make sure you're following our Facebook in particular if you want to be informed about those so you can actually get a project done over summer. We also have elections coming up, and there are many non-technical roles. You might be interested in data science, but not too experienced with it. That's fine. Check out the link here. Loads of things going. We're a very fast-growing society. I think we've more than tripled our size in the last year. So please do check out what roles are going. So the structure of the session. Actually, I think that was just there for me. We don't actually need that anymore. Okay, and if you like this talk, we have more content like it. We did a talk at Warwick Women in Finance about a year ago, very similar to this, talking about how you can use Python and machine learning for predicting kind of finance-based problems. And we have a series of beginners tasters, just short sessions, introducing some data science ideas. One is about visualizing your Spotify playlist, kind of making a wall of all the cover art that you listen to organized by genres. And another one's about predicting football scores. So check that all out. Okay, so today's session is all about machine learning. And so I kind of want to start by asking in the chat, kind of how much do you know about machine learning? From 0 being you've never even heard the word before, to 10 being you're an expert in it. Where would people place themselves, just so I have an idea? So please, if everyone can just pop in the chat, 0 to 10. Okay, great stuff. Okay, so might have heard of the idea, might know a bit about it, but still trying to build up some familiarity. That's brilliant. And thank you everyone for responding. All the questions I'm going to be asking are going to be very open, so if everyone answers, it's much easier to carry on with that. Okay, so at a high level, what is machine learning? It's basically... Sorry, was there a question there? I guess not. So they're basically algorithms used, and they're based on statistics, try and automate finding patterns and trends in data. So we have some data we want to understand kind of what patterns are going on, what trends are in there, but we don't want to do that manually. We want to automate the process. That's what machine learning is for. And so a few examples of what machine learning might look like. Recommendation systems. When Netflix or Google recommends a film or a web page, they're using machine learning to decide what they think is best for you. Computer vision, so things used in self-driving cars, that is using machine learning. Reinforcement learning, stuff like AlphaGo or any AI that is used to play a game. That's a type of machine learning called reinforcement learning. Dimensionality reduction, maybe we have data that has thousands of dimensions, really colossal data. Think the sort of stuff that in Facebook, for example, they'll have so much data on you, so much that a human can't understand it. How can we collapse that down into a simpler representation for humans? That's a type of machine learning. And finally, clustering. So if I have loads of data on my customers in a shop, I want to figure out, are there some groups of customers that have similar behavior, that buy similar things? That, again, is a machine learning problem. So it's a really wide range of things we can do with it. The general idea is it's automating pattern recognition and discovering of trends. Okay, so we're going to start by going through a bit of terminology related to machine learning before getting into actually fitting a machine learning model for ourselves. So there are loosely two main types of machine learning. There are way more, but these make up 99% of the use cases. And they are supervised and unsupervised. And the main difference between these is whether or not we have labeled data. So supervised learning is when we give our model, our machine learning algorithm, data that has labels attached to it. So a human perhaps has labeled those. Whereas unsupervised learning is giving it unlabeled data. So there's no correct answer. We're saying just find what you can. But with supervised, there is a correct answer, and that's the labels we gave it. And so the objective of these differs. For supervised learning, we're all about predicting what the labels are going to be on new data. So we give the model some data with labels, we then give it some data without labels, and we ask it to predict what those labels would be. And in unsupervised, there's never any labels. We just say, hey, just find the patterns. Whatever those patterns happen to be, tell me what those are. So an example of supervised learning might be image recognition. Is this a picture of a cat or a dog? There is a correct answer. But unsupervised might be, here's all my customers. Can you just split them up into some high-level groups that define their behavior? So there's no correct answer here, but we can still detect patterns. And so supervised learning is the more popular one. It tends to be a bit easier. It's very well studied. But unsupervised learning is having more and more potential as we get access to more and more unlabeled data. You can imagine all of the text on the web. No one's kind of labeled that into clearly defined labels of what this is talking about, but you might be able to gain insight just from looking at the text as it is in an unlabeled fashion. So kind of a description or like a diagram showing what these might look like. Supervised might be we're trying to take our data and predict whether it's one class or another. Is it a cat or is it a dog? Whereas unsupervised, there aren't any of these labels. It's all unknown, and we just try and group them into similar clusters. Okay, so in this session, we're going to focus on supervised learning, so trying to predict the labels of some data. And so when we talk about supervised learning, there are two subcategories, or two main subcategories that we're interested in. So the first is regression, and this is when we're trying to predict a continuous value, so a value that can be a decimal number, say. So this might be the price of a car. A car could have any price from 0 up to infinity. So Yeah, the important thing here is that there's no kind of distinct values, there's just a spectrum of all values it could be. Classification, on the other hand, is when we're trying to predict a category. So there's not a spectrum, there's single values that it can and can't be. So an example of this might be the type of a house. Is it detached, is it semi-detached, or is it a terrace house? There's nothing between a detached and a semi-detached house, and they're fixed categories, and we're trying to predict what those categories are. And so, like in a diagram, it might look like regression is trying to kind of fit a line that maps, our inputs to our outputs, and classification is trying to split our data into two or more distinct categories. Okay, and so, yeah, let's kind of just pause for a second and ask people, just so we can see kind of if people are following along, if you have any other examples of what a regression problem might be predicting or classification. If people just want to throw a few examples of kind of what regression might be, what classification might be, just so we have some other examples.
Dead life.
Okay. Yeah. I guess everyone seems to be a bit nervous on that, so that's completely fine. We'll carry on with that. But another example might be if we're trying to predict, the location of something. That would be predicting a latitude and a longitude. Those can have any value, so that would be regression. But something like predicting someone's sex, male or female, that would be classification because there's only two values that can take. Okay, so when we're performing supervised learning, the goal is to predict what the label's going to be for each data point. So we're given the labels to the model, and then from that we have to learn how to predict them in the future. And so we call the thing that we're trying to predict the response variable, and the values we're using to predict the predictors. So we have the predictors, and you can almost think that the thing we're trying to predict responds to the values of whatever those predictors are. And so we call that the response. So that's enough terminology. Let's get into the actual, the main bit of the machine learning. So there are many different types of machine learning models, but we're going to focus on a type called random forests. And the reason for this is as follows. So we can use them for both regression and for classification, so predicting continuous things or categorical things. They work with a wide variety of different data types. They work pretty well from the start, so we don't have to kind of fine-tune them and kind of figure out exactly how to make them good. They're pretty good just out of the box. And they also generalize pretty well. So if we train them on some data and then try them out on some unseen data, they tend to do pretty well, whereas other models can struggle to generalize. So let's kind of introduce what random forests are through these things called decision trees. So a decision tree is basically a process you use to decide what an outcome should be. So one example of a decision tree might be predicting whether you should take the bus or walk to work. So the first question we might ask is, what is the weather? Is it raining? Is it cloudy? Is it sunny? If it's raining, we definitely take the bus. If it's cloudy, for some reason, this isn't my graphic, it depends on whether we're hungry. I guess we can probably stop and get something to eat. And if it's sunny, we decide based on the time. If it's going to be a short journey, I guess we'll take the bus, or is it how long we have? It doesn't really matter. The idea is there's this process that we follow to decide what the outcome should be. And so these things in blue are our predictors. We're using this to predict what the outcome should be. And the response is this kind of categorical variable. Are we walking or are we catching a bus? So this one here was generated manually. And so this isn't much use for machine learning, but the idea applies to machine learning too. But when we use it in that context, rather than manually deciding what the tree should be, we try to learn it based on the data. So we give our machine learning model loads of examples of what the inputs were, what the predictors were, and what the correct response should have been. And it's going to learn what the best tree diagram is going to be to get the outcome. And so we give it more and more data and it'll learn that better and better. So if you want to know exactly how this is done, this is a technical detail. If this doesn't make any sense, ignore it. But the way it does it is that it looks at all of your variables and tries to figure out which one, if you split on it, would have the most potential for separating your responses. So what has the most predictive power? And then we split on that. So in this example, it's going to be the weather was the most important. We split on that first. And then we just repeat that again and again and again. So for each subset, we then find the best split and split again. And we don't have to worry about how we do that. We'll see later there are tools in Python to do that all automatically. So decision trees are pretty cool. There's a visual example here if you want to follow this link. We're not going to go through it in detail here, but it's a walkthrough of decision trees in this amazing visual way. So it's definitely worth checking out if you want to kind of really understand what a decision tree is doing. It's really impressive. Okay, so decision trees can also be used for regression. So when we're predicting a continuous thing, but in that case, rather than ending these nodes with like a categorical value, like walk or bus, we end each of them with a number, which is our prediction of what the corresponding value should be. So these are very general tools, very useful, but there is a problem. That these models tend to overfit. And what I mean by overfitting is rather than learning the patterns in the data, they attempt to memorize the data. And so you can imagine this like a person preparing for a test. Let's say you have a set of 10 questions that you have to practice and then an exam with 10 other questions on it. One approach you could take is to look at those 10 questions you have to prepare with and just memorize the answers for those. That would be a really bad idea because if the questions on the actual test are different, you're screwed. You've learnt nothing. If instead you try and learn kind of the general ideas and the patterns in those kind of practice questions, then you'll be better equipped for the final thing. And so decision trees have the potential to do the former thing, just memorize the data and then be useless when you have any new data. And this is known as overfitting. We've overfitted to the data that we're training on. And so an overfitted tree might look something like this one on the right. So here we're fitting a model that tries to learn whether someone uses the word life hack or top tip based on their age. And a sensible kind of well-fitted model would look something like this. That if you're under 40, it's probably life hack. If you're over 40, maybe top tip. But if we let this tree grow too big, then we end up with a way too complicated model that hasn't actually learned what the pattern is, but learned to memorize the data we trained it on. So maybe there was one person who was age 28 who said top tip, but they were just an outlier. They weren't part of the actual trend, just random chance. But this model has learnt that as if it's ground truth. So this is really bad and would do terribly on a new set of data. Okay, so what can we do about that? Well, the answer is random forests. And so, kind of as the name suggests, a forest is a collection of trees. And so a random forest is a collection of decision trees. And the idea is that we take our data set and we train a tree to try and predict the outcomes. But we only use a subset of the predictors and of the observations. We only use certain variables for predicting, and we only pick out certain rows of our data set. So if we had 100 people, we'd only use half of them each time. And we do this again and again using random predictors and random observations every time. And because we're not using all of the data, it makes it much harder to memorize the whole thing because there's less data to work with. And so it's harder to memorize and they're therefore harder to overfit. So all these trees are less likely to overfit, but they're weaker because we're not using the whole thing. Okay, so there's a question here about how we would use decision trees for regression. So you'd only get as many possible values out as there are leaves in the tree. Yeah, so the number of leaves tends to be pretty big. But the idea is like there's a lot of noise in your data anyway. You'd never be able to predict it perfectly. And so even if you only predict, say, 20 different values, you predict 2 for some of them, 7 for some others, it doesn't really matter because the amount of error you have from not being precise in your answers is very small compared to the amount of noise in the data. So only in a case where you could perfectly predict the outcomes would that be a problem. But in almost all machine learning problems, it's impossible to fully predict the outcome just because there's random noise or people don't behave consistently. Okay, so yeah, the idea is that we fit a tree again and again and again on subsets of the data. Now, because we're using subsets, it's harder to memorize the whole data set, but each of these trees are pretty rubbish because we didn't give them all of the data. So what we then do, when we want to predict, we ask each tree to vote on what they think the correct answer is. And then we take all of those votes, aggregate them together, and whichever one had the most votes, whichever outcome had the most votes, that's the one that we use as our prediction. So you can think of this as like how, I guess that's how any voting system works, maybe in a company. You have loads of specialists. One has used all of the data on people's ethnicity. One knows an awful lot about their employment. One knows a lot about their sex or social profile, whatever. And each of them have their vote on what they think the answer is. Each of them are pretty rubbish because they only have kind of small ideas about the data, but you combine this all together and you get a good answer at the end. So these types of models are known as ensemble models because ensemble means, all together, or like an ensemble in music is like a load of different instruments. It's that kind of idea, loads of things together that are powerful when combined. And so we can use as many trees as we want to. Generally, if we have more of them, we get better predictions, but it takes longer to train the model because every tree takes time to train. Eventually, the curve will flatten out. There's only so well we can do. That's just the limitations of the data itself. So we need to find that happy medium between enough trees to do well, but not wasting our time getting very little extra performance. Okay, so now that we've kind of introduced those ideas, I'll just pause for a moment if there's any questions, but after that we'll move on to actually fitting this and making a model using Python. Okay, if there's no questions, then we'll carry on. So the first thing we're going to do is do some imports. And so what I mean by this is there's no point reinventing the wheel. The ideas we're using are quite complicated. I wouldn't know, or I'd struggle a lot to make the code to fit one of these random forest models. It's hard. But the beauty of using a language like Python, which is very popular, is that someone's done it for you already. And so we can take these really powerful existing tool sets and use them in our code and just worry about the high level things. And so this is what we do at the start here. We import various different packages. So we have NumPy, which is used for doing maths, pandas for data manipulation, matplotlib for kind of visualizing and making plots, and then all of our machine learning ones at the bottom. So the way we run some code in Colab is we just click the play button. It's going to give us a little warning, that's fine. And then that has been run. Another way to do it is Control and Enter if you don't like using your mouse. So now we have access to all of these tools and we can use them in our workflow. So a few things just to bear in mind if you are following along with this code as we go. So Python is case sensitive. So if you type something like NumPy with a capital N, it's going to give us an error, because it's expecting things to be written with the exact right case. So make sure if you're copying my stuff out that you get the case correct. That said though, Python generally doesn't care about spaces or new lines. So I could put a load of spaces in here and a new line. I think it will read that just fine. Okay, it didn't like the new line there. But generally, spaces are always all right, and new lines can most of the time be added. So don't worry too much about getting that exactly correct. And as I mentioned, you can use Control-Enter to run something kind of a faster way. Okay, so what's the data we're going to be working with today? So we're going to be working with a data set that contains numerous characteristics of adults from the USA. So we have information on their sex, their race, their age, how much capital gains they had in the year, their education level, loads of things. And then whether or not they earned more or less than £50,000. So $50,000 even. So we're not trying to predict how much they made. That would be a regression problem, the exact value. We're just trying to predict, it's categorical, did they make more or less than 50,000? And so this data comes from the UCI machine learning repository. It's an amazing site with loads and loads of data sets cleaned and ready for machine learning. So you could maybe even take the things we look at today and try them on predicting breast cancer or the price of cars. There's loads of things you can do with this. If you do want to have a go at those things, the Data Science Society is running a code night on week 9. If you follow our Facebook, you'll be notified about that. You can come along to that. We have all of our exec and loads of people who know a lot about data science. You can have a go at one of these other problems. Maybe there's a certain one you're interested in. We can help you out with that. So please do check out our Facebook to learn more about that. So that is the data, where it comes from. But I've made a cleaned up and kind of like pre-processed version that you can download from here. So if we follow this here, and it's going to just open this file here, we can right-click and save as, or we can use Control-S if that wasn't there, or Command-S on a Mac. So we can save that, and we'll just put it, say, in our downloads, and we're going to call it, well, the name it's given here, adult.csv. So CSV stands for comma-separated values. You can see the data here is loads of different values. So each row is one person, and the values are separated by a comma. So we have their age, the type of work they do, their education level, all separated by commas, which is why it's called comma-separated values. Okay, so we can now upload this to Google Colab. So if we click this little file icon on the left-hand side, we can click the upload button, there's a little up arrow on a file, and then find the dataset, adult.csv, and upload that there. So it gives us a little warning saying this will be deleted at the end, but that's completely fine. So that's going to take a second just to load up, but once that's done, we'll see it appearing here. So we need that dataset on Colab to be able to import it into Python. So now that that is done, hopefully, there we go. We can just close out of that. Okay. So now is where the coding starts. So we're not going to worry too much about what all the coding is doing. Can you wget? Yes, that's completely fine. So if you want to do any bash commands or scripting in Colab, you start with an exclamation mark. So you can wget and the address like this. So anything you want to do on the shell level, like ls, you can use an exclamation mark to start that. If you don't know what that means, no problem. That's just answering a question there. Okay, so we're going to actually start importing things. We're not going to worry about exactly, where our code came from, but more at a high level what it's doing. So I've made here a list of the column names. So if we look back here, the data actually doesn't have any column names inside of it, so I had to manually write those out. So this is just creating a list of the column names. You'll see this equals appearing quite a bit. And this is called assignment. Basically, we take the value on the right and we give it the name on the left. So if we want to refer to this later, we can just use column names. Actually, we can give an example of that. If I run that and type out column names, we'll see that column names just points to that data. So it's just a name for that data there. Okay, so we're going to import our data into Colab. So the way we do this is with pandas. So when we imported pandas, we gave it the name PD. So we're going to use that to refer to it. And the command is read_CSV. And then we follow this by, in quotes, so you can use double or single, they mean the same in Python, the name of the file. So it was, what did we call it? It's at the side here, adult.csv. That's the name of the file. And then we're going to need a few other things. So we're going to pass in the names of our columns. That's going to be column underscore names. So the names we're going to use for our columns is equal to this value column names we made earlier. And finally, we need to add this thing called na_values equals, then in quotes, a question mark. And what this is saying is that at various points in our data set, we have question marks, and these represent a missing value. And so we need to tell Python, or tell pandas, what symbol we're using to represent missing values. And so these are called NA values, NA standing for not available. So they're missing, we don't know what they are, and we're using a question mark to represent those NA values. So if we run this code here, we get the data set. But what we're going to want to do, rather than just displaying it, we want to give that a name. And so we're going to call it income underscore df. So that's a df for data frame. And we're going to set that equal to the thing we just imported there. So this is now a name for this data that we imported. So we can run that, and now we have that income data frame in our environment. Okay, so this data set comes with two columns that we don't really care about. That is final weight and education. So final weight tells us it's an estimate by the researchers that made the data set of how many people in the country have the attributes demonstrated by that row. So basically, how kind of common is this person? And education we don't need because we also have their education as a number. So education is okay, yeah, so not sure if that's a question there, but anyway, so we have that education, and this is as kind of text. Is it high school diploma? Is it bachelor's? Whereas here is a numeric one, going 1 to 18, giving the level of that education. And yeah, oh yes, if people do want to copy and paste, if you go to this one here, at the top of the link, this is just all completed, so you can copy it from there. Okay, so yes, there's two versions of education, and the one that also includes their ordering is kind of more informative. So we're going to get rid of the normal education one. So we can drop these unnecessary columns, and the way we do this is with income data frames. We take that data frame, and then we use dot drop. So this is saying I want to drop some columns. We put the column names in square brackets, and we put each of them inside of quotes. So the first one we're dropping is final weight, and then separated by a comma, education. So we're dropping these columns, and then we have to tell it, are we dropping rows with that name or columns with that name? And we set that using the axis parameter. Axis 0 is rows and 1 is columns. So we're getting rid of the columns that have these names here. If we run this, we get a new data set without education and without final weight. And so now we can take that and just assign that again to the same data set. So basically take this new version and now have this name point to the new version. So we're kind of updating it with that new one. Okay, so I've got rid of that unnecessary column that we didn't really care for. So what does this data look like? We can print out the dimensions of the data. So we would use income data frame dot shape. So what is the shape of my data? And we see we have about 50,000 rows, so a lot of data to be working with, and 13 columns. So that's 12 predictors and the one response we're trying to predict. And so we can print out the first few rows. The command for that is head. So take the data frame, and you can think the head is like at the top of your body, so it's asking for the top of the data set. We run that, we can see a snippet of the first five rows. So we have people's ages, what kind of type of work they're doing, whether they're married, their race, sex, the country that they're initially from. And so I'm going to take this point to pause and ask people, we're going to try and predict what the income is. Which of these variables do you think is going to be the most important? Well, we'll actually see at the end what our model believes to be the most important. So if you want to have a guess in the chat, which of these do you think is the most important for predicting what someone's income is?
Occupation.
So we're not going to use income. So we're using these first 12 to predict the income. So obviously, income would be very good for predicting income, but they'll be cheating a bit. Okay, so people think occupation is quite an important one. Any other guesses? There is no right or wrong answer. In fact, the answer surprised me a lot. I got it completely wrong. Okay, so we're thinking things to do with working and education. So what sort of job they do and what their education is. Okay, I guess we'll see if that's correct later on. So let's have a look at what data types our columns have. So we do this by typing the name of the data set, so income df, and then we use the command dtype for data types. It didn't like that. Dtypes with an S? Yeah, dtypes. Cool. So we can see here all of the different types of data that we have. So a float means a decimal number. So basically a number that has a decimal place. Object means text, so text data. So we can see that we have a few integers. Those are our whole numbers, such as your level of education, your hours per week. We have one float, so one decimal number, which is your age. You can see the decimals here. And the rest of them are all text. So we have your marital status as like a label, as text. Okay, so some numeric and some text columns. Let's summarize the numeric columns to see what sort of range that they have. So we can take income data frame and use the command describe to describe the data set or describe the numeric columns. And this gives us how many values there are, the average values. We can see the average age in our data set was about 38, the minimum, the maximum, and some other quartiles if you're familiar with them from statistics. So the ages were between 17 and 90. The biggest capital gain was almost 100,000, and the biggest capital loss was also pretty big. So that's for the numeric columns. Can we ask anything about the text columns? We can. We could, for example, ask what the unique values are in a certain column. So we can take this income data frame, pick out a certain column using square brackets. So the way we pick out a certain column is square brackets and then in quotes the name of the column. So one column we might want to look at is the native country. So we type out native country, and if we run this as it is, we get the whole column. We just want the unique values. So we put a dot and then unique, asking for the unique values there. And we see they're United States, some various other ones too. So quite a wide range of them. And Holland spelled incorrectly, peculiar. And so we can also create some plots. We're not going to walk through this code here. If you click the play button or control enter to run it, we get a plot of age against capital loss. So, I mean, not the most informative, but we can do that if we wanted to. And if we had more time, we'd look at some other plots that we could do. Okay, so typically we want to split our data set into the predictors, so the data we're using to predict the outcome, and the response, the thing we're trying to predict. And we normally call these X and Y. And so we're going to create X by dropping the income column. So X is going to be this data frame, income df, after we've dropped the income column. And the axis is 1, we're dropping a column here. So this is going to be everything in the data set except for income. And our Y is going to be just the column income. So as before, square brackets and then quotes. And so we now have two data sets. One is our X, everything except for income, and then Y is just the incomes. Cool. So we're now going to get on to cleaning up the data. So we mentioned before that the data set has missing values. Let's find out where those missing values are. So we can do that by using, so axis equals 1. This means column. So when we use dot drop, we can either drop rows or drop columns. If we use axis equals 0, it's going to try and drop a row, but there isn't a row called income. So it's going to get confused. Instead, we try to drop a column called income. Cool. So where are the missing values? We can take we're now going to use X rather than income df, so just take our predictors and ask is.na. So is this value NA means missing, not available. And then we're going to ask, are any of them missing? So if we run this, it's going to give us for every column whether any of them are missing. So we can see we have missing ages, missing work class, but all of our educations, all of our marital statuses, they're all there. It's false that any of them are missing. We can see how many are missing by using sum. So we kind of sum, kind of add up, count how many there are. We can see there are 2 missing ages and a lot of missing occupations and work class. And so actually, now that I think about it, maybe this is actually, the fact that they're missing is important. Perhaps people that are unemployed have an occupation that's missing. So maybe it would be important to take that into account, but I haven't. So we'll forget that for now and just ask if any of them are missing. Okay, so we have missing values in both text columns and numeric columns. So age is numeric, that's missing values, and the occupation was text, and that was missing values too. So we're going to have to handle these in different ways. So we'll start by replacing or handling the missing values in numeric columns by using the column mean, so the average value in the column. And so the command we use for this is we're going to take x and we're going to fill the NA with the mean of x. So this means take every column and calculate the mean, and then we're going to fill the missing values with those column means. It's only going to do this for the numeric columns. So this gives us a new one without any missing values. It takes a second to do it. And we can take that and we can assign that to x, basically replace the old value of x with this cleaned up version of it. Cool. So that's all of the numeric values sorted. What about the text ones? So there is no kind of average or mean of text columns, like, how do we add up different bits of text? So instead we have to use the column mode, which is the most common value. So you can imagine if our data set, if we're missing someone's country, our best guess would be they're from the United States because that made up the majority of the data set. There are much smarter ways of handling this, which we'll get to in a second, but we'll just take the most common one for now. And so this is the code to do that. I'm not going to explain what it does because it is a bit fancy, but we can just run it and that will replace them with the most common value in each column. So now we can take this code from above where we asked, are there any missing values? Just copy that, run that again, and we'll see, no, there's now no missing values. We've cleaned that all up and we're looking good. So if you want to see a deeper discussion about missing values, episode 5 of the Data Science Society's podcast, Data Basic, we have a good discussion about missing values and how to handle them. Yeah, so actually that's a good question. So if we are assuming that the missing value means unemployed, can we just replace it? And so yes, you could, but it's probably not the best way to handle it. The best way to do it would be to replace it with the average value, so replace it with the most common thing, and then create a new column which was 1 or 0 depending on whether the value was missing. Because we don't know for sure if missing means unemployed, it's just a guess. So we shouldn't assume that. We should give our model some information to use, that it can decide to use that if it wants to. We don't force it to use it. And so I think we actually discussed that in the podcast, so do check that out if you want a more thorough discussion of how to handle that. Okay, so now we have a cleaned up data set, but it's in kind of a form that's not very friendly. So if you go to this website here, we have RSS, Spotify, and iTunes. So we now have a data set which has a lot of text columns and numeric columns. But machine learning algorithms tend to prefer numbers. They're just much easier to work with. And so we need to encode, that's kind of a technical term, our text columns into some numeric form, so turn them into numbers. Loads of different ways we can do this, but the most popular one is called one-hot encoding. Sounds fancy, but all it is we take a column, like sex, that has certain values, and we make a new column for each of the values it can take. So for male and for female, if there was another sex, we would put that at the end here. And then if the original one had a certain value, we put a 1 in that column, otherwise we put a 0. So now, this is a two-way thing. We can retrieve the original thing from here, or we can go from there to there. It's the exact same data, but now everything is numeric. So this is called one-hot encoding. It sounds quite complicated to do, but we're lucky because sklearn, which is the package we're using for machine learning, has done it all for us. So first we have to pick out our text columns and our numeric columns. So we'll start with the numeric ones, and that's going to be selecting data types and we're going to exclude anything with object. So object was kind of pandas, or it's NumPy's term for text data. So that's the numeric ones, and the text ones are going to be the exact same thing, but we're going to include the object ones. So we've now split our data set into the numeric ones and the text ones. Cool. We can now encode the columns using a one-hot encoder. So the way we do this is we create an encoder using the function one-hot encoder. So this comes from scikit-learn, this package for machine learning. So we create an encoder, and then we use encoder fit_transform, and then pass in our text data. So this means fit the encoder, and then do the transformation into this new form here. And then we're going to take the output of that, and then we're going to call that text_enc for kind of the encoded text. We run that, and we now have an encoded version of the text. We can now recombine our variables together. So take the numeric ones we had before and these new text ones, we combine them together, and we also want to kind of keep note of what the new column names are, because we now have more columns than we had before. Like the column before was called sex, now it's kind of a column for the values that column had. So this code here creates the new names of our columns. Okay, so that is x encoded as numbers. What does x look like now? So it looks a bit different to before. So before we had this data frame, but now it's just one giant matrix of numbers. So a two-dimensional grid of numbers. And the reason for this is that it's more efficient. Now that all our columns are numeric, we don't need a data frame. Data frames are when you have different types of columns. When they're all the same, we can have it in this one massive matrix where everything is a number. So that is what x encoded looks like now. Okay, we'll also do a similar thing for y. So we're going to replace y with a 1 if it's bigger than 50,000 and a 0 if it's less than. So we ask, is y equal to less than 50k? And we take this and then we just convert it into a number, so to turn it into an integer. If we run that code here, y encoded looks something like this, just ones and zeros. Cool. So we're now ready. Oh yeah, we're not ready just yet. We'll almost be doing the machine learning. We need a way of checking whether our machine learning model is actually working. So we saw before that models have the potential to overfit. That's when they only learn the training data and don't generalize to new data. So we need a way to get around this. And what we're going to do is we're going to split our data into two parts, a training part and a testing part. We're then going to train our model on the first bit, this training bit, and then evaluate its performance on the second bit, which is the test set. So because we're testing it on unseen data, we'll be able to tell if it memorized the data. So if it just memorized the first bit, it will do terribly on the new data, and we'll know that we've overfitted. If it does about the same on both of them, then that's really good. Our model generalizes to unseen data. And so we can do this using the function train test split from scikit-learn. So the command is train test split, and then inside of here we're going to put our predictors and our response. Say how big we want the test size to be. So I'm going to say 0.2. So use 20% of the data for testing, 80% for training. And then we're going to put in a random state. And what this means is that these training test splits are done randomly, but it would be good if we all had the same random thing. So the random state just means it's kind of the starting point for the randomness, so we all end up with the same thing at the end. So if we run this, we now get our data set split into train sets, test sets, and we can use one for training and one for testing. And so before we fit our model, it's worth asking what a good baseline would be. So how well could we do if we were just guessing? And so the most simple model we could make would be to ignore the predictors entirely and just predict whatever the most common outcome is for every observation. So if we look at the counts of the variables in y, we see that the majority are less than 50k and about a quarter of them are greater than 50k. So the simplest model we could do would be just to predict less than 50k for everything. And if we did that, we would be right about 75% of the time. So if we can make a model that's better than 75%, then we're doing well. If we're doing worse than 75%, then something's gone wrong. Okay, so let's now build the model. So, yeah, we're now ready to make it and fit it to the data. So we're going to start by making the model, and the code we use for this is random forest classifier. So this is just a function from sklearn that allows us to make a random forest without worrying about actually how we do it, followed by brackets. And we're going to save that to the name CLF, short for classifier. So this is our classifier, and now we can fit it to the data. So take the classifier, use fit, and then we're going to pass in our training X and our training Y. So we only fit it on the training data, and then we'll evaluate it on the new data. So we run this, it's going to take a second. So what didn't it like about that? Could not convert string to float private. Okay. Oh, sorry. Wait. What have we done wrong here? Okay. Back up to here. We should have used the encoded ones. So we made our test and train split using the original X's when we wanted the encoded ones instead. So we have to change this back to the encoded ones, make the train test split again. This should be the same, but that's 1 and 0 because that's the encoded ones. We can now fit the model again, and it'll now be happy to do that. Okay, so it takes a while to do it. We're fitting, by default, 100 trees. And these are kind of the default parameters that it uses. We don't have to worry about what these mean. Okay, so now that we've fitted the model to this data, we can make some predictions. So let's make predictions for the training set and for the test set. So our predictions for the training set are taking this classifier and then using predict on the training set. So we predict with our X training data. Then we'll do the same again for our test predictions on the testing data set. So now we get sets of predictions for the training and for the test data set. And just to see what those look like, let's look at the test one. It's just a series of 1s and 0s, mainly 1s, or at least at the start and end. Okay, so we made those predictions. We can also ask how important different features were for the model. This is some kind of advanced code, so we're not going to worry about what it does. We'll click play and we'll see the answers. So these were the most important features. So importance is how important they are, and we can see they're decreasing here. So the most important was actually age. That being, whatever your age is the most important one for how much income you have. Followed by education. I think someone guessed that, so very good. And then your occupation and working class are fairly important. And it seems that actually your sex and race, probably because of discrimination laws, aren't as important on predicting your income there. Cool. So we've made a model. Let's see how well it does. So we can compute the accuracy of our model at predicting the income. And the way we're going to do this, we're going to ask how many of the predictions for the training set are equal to the actual Y's for the training set. And we're going to take that and we're going to calculate the average with .mean. So on average, how often do we get this right? How often are these equal? And we can do the same sort of thing for the test set. So we're going to do the predicted tests and the actual tests. So we run this and we see we were 97% accurate on the training set and 85% accurate on the test set. So we'll come back to that in a bit later. And we can also plot what's called a confusion matrix, which shows where our model is making its mistakes. So if we run this code here, we get two confusion matrices, one for the train set, one for the test set. Oh, it's done it in scientific notation. That's very annoying. Okay, hopefully people can read scientific notation. It's weird, it didn't do that on my computer. And so we can see here that when the true label was less than 50k, about 8,000 of those were predicted to be less than 50k, and about 600 of those were predicted to be greater than 50k. So you can see where it's making its mistakes, but most of the time it's on this diagonal, which is where it's correct. So it's a pretty good model. Now, the problem we see here is that the training accuracy is much better than the test accuracy. And so it appears a bit like our model is just memorizing the training set and doesn't generalize well to new data. And there's kind of a diagram explaining this where if we have our model complexity at the bottom, here we have our training error, and here we have the error on our test set, the training one will always decrease. As the model becomes more complex, we have more ability just to memorize the training set. But as we memorize this more, we stop being able to generalize. We've overfitted to the training set, and our test predictions get worse. And if we have a very simple model, it's bad for both of them. So we want to find the optimal point here where they're both pretty good. So we can look at the documentation for the random forest classifier, and we can see there's loads of parameters here, or if we look through the list here. So for example, there's the maximum depth, and by default this is none. And that means our trees can be as deep as we want them to be. So we can keep making splits in the trees until they're really, really massive. But I might want to say that actually, I only want my trees to be 10 nodes deep. And after that, they're too complex, they're just going to make the predictions worse. So when I go to predict, when I go to fit my model, right back up here, I can add parameters such as max depth, maybe set that to be 10. So now I'm saying they can only be, so it doesn't need much modification. This is pretty good by itself. It's done 85% accuracy. That's much better than the 75% that we would have got by random guessing. So it's done very well, but we can always make it better. So we'll see that when we actually try to make it better, we only make it slightly better. So that's kind of the point I'm trying to get across. It does pretty well by itself, but we can still improve it. So one thing we might want to do is say I only want trees that are 10 deep. That's going to stop it from being too complex. I'll run this now. I will refit it. I'm going to predict again. The importances will probably be the same. Oh no, wow, they've completely changed now. So now that we're only allowing simple models, the marital status is now more important. So that's an interesting thing by itself. We don't have time for that. We can now predict again, and now we'll see we get 86% for both of them. So our training accuracy is worse. That's okay, because our test one is better. But we'll see it's only better by about 1%. So really, the initial model was pretty good. And we've only made a slight improvement here, but a small improvement is still an improvement. And so with that, we're going to wrap up the session. But I'm going to leave kind of a question for you to ponder. How well can you do? So if you have a look through all the parameters here, there might be other ones you want to try. Maybe try different max depths, different min samples leaf. Just try different values. You can look at kind of the description of them to see what they do. See if you can get better than this here. And maybe you can get up to 90. I'm not sure. But that's something for you to play around with. And as a reminder, if people have joined late, if you click at the top here, this is a completed version. You can go onto this, click runtime and run all. That's just going to run the whole thing so you can see the outcomes for yourself. So with that, thank you everyone for coming to this session. If you want more stuff like this, make sure to follow or like Warwick Data Science Society on Facebook. We have loads of events, loads of teaching, all free and very high quality. So thank you for coming. See you soon.